tools. I'm trying to install Matplotlib. No background removal today. If anyone knows any alternatives to ChromaCast or anything that works more reliably with OBS, then I'll be really happy to do that, because ChromaCast has just proved to be useless. Just fails to start continuously. So what are we doing today? So what we're doing is we're basically digging a bit deeper into the VQE and the VQE constraint stuff. I mean, it's just VQE is like the standard VQE, right? It's just that one of the things that I came across last time, why is it taking so much to delete imports? Do you import these like this? I guess so. But I came across these, so I was kind of asking like, okay, so how do you do even gradient descent on a quantum circuit? How can you do that, right? Like I was not totally right when I said you don't know the function. You do know the function because you kind of have your circuit, right? So it's just a multiplication of gates, and those have their matrices. And so, like, if you parameterize the matrices, then you kind of have the equation. So you have the stuff you want to derivate, right? Like, I wonder, can you derivate a matrix? Can you matrix? So derivate, differentiate, not derivate. Sorry, that's my English. Can you differentiate a matrix? The derivatives of matrices that can be organized into matrix of the same size. Interesting. I didn't know that. The derivative of a matrix by a scalar and the derivative of a scalar by a matrix. Okay, so it's just the derivative of its components. Okay. Looks like. Anyway, but it's still like you kind of have you can have a really big matrix, right? Like if you have a lot of qubits, so it wouldn't be just practical to do that. But then I came across these thing from Xanadu where they talk about the parameter shift rule, which basically, or penny lane, yeah, which basically says that, oh, that's a comment. What is these? Is that a mirror? I guess so. And the combination of function rules talks about constructing partial derivatives by evaluating the same circuit with different parameters. How is this any different than numerical differentiation, though, mentioned here? What's an example of? Computers. Yeah, I think I remember reading these here, right? Where no, that's not what I wanna, that's not where I wanted to go. Parameter shift rules. There you go. So this is what I was reading. This is what I was reading the other day, and I was like, okay, so basically what they're saying is that you can, so the derivative of your quantum circuit is just like you can do that, express this in this way, just by like taking two angles, like two different parameters, and then just subtracting, and then you get the derivative, right? And what caught my attention is these, right? So it's the fact that you, so apparently, if you make, it's similar how the derivative of the function sinus of x is identical to like a half of sinus x plus pi divided by 2 minus a half of sinus x minus pi divided by 2. And I wanted to I kind of had the idea to first of all try to visualize these with SymPy, and then second of all try to kind of do the same with the quantum circuit, basically. Start with a very simple one, and then try to kind of visualize the expectation value, and see whether that becomes somewhat intuitive or obvious that it's got to be this way. I mean, you can go through the full math, but basically it seems like that's where you're getting, right? So okay, so there's an example here, and But let's see. So if I, well, that's still running. I don't understand that though. Maybe I should just kernel restart and run all. How do I plot stuff in Matplotlib? Examples. Just want to plot something like dots or something. Like plot a matrix. Plot a matrix. Matplotlib. Math show. I don't want to. No, sorry, I don't want to plot a matrix. I just want to plot a. Just plot like. I'm lacking the language. I just want to plot like the, because that's going to plot a matrix. Like it's going to actually plot a grid, and I don't want to plot a grid. I want to plot a just dots. Maybe this is just categorical variables. No. Just a scatter plot. Okay, maybe. Scatter symbol. Scatter plots with a legend. Simple plot. Stem plot. Maybe something like these or something like these. So what do we do here? So you have, so you import these, and then you kind of have oh, so you just okay, so you just have a function, give it a value, give it a range, and then just plot the thing. Okay, cool. Let's see if we can just do that. We'll just do these, and then we'll just I guess I just want that, and I just want the we'll just get everything. Why is it still running though? And what I just don't want to have, like, I don't care about the axis right now, and I don't want to save this. Just want to run that. But why is this taking so long? Have I installed Matplotlib wrongly or something? Why is this taking so long? Successfully uninstalled Matplotlib 3.1.1 and installed this one 3.3.2. So I already had it installed. Okay, but it doesn't. Maybe just should. Maybe I should just do this. Install Matplotlib. What does this do? Does this install it like? I guess globally. I don't know. Let's see. Or is available? Okay, yeah, but everything seems to be there. It's just why does this take so long? Kernel entrapped. So what happens if I just comment this out? Something's off with my internet connection, maybe? No, it's not, because I'm just like, so what's the issue with these? Maybe with Jupyter? It took a while though. Why? Oh, now I have no idea. I really have no idea. Okay, cool. But now it worked. So, but if I just do like the, so what are we trying to do? So we're trying to basically take a look at, not these, but like take a look at, where's the whole, where's this guy? So this is here basically. So we are having these, and let's plot these. Okay, so let's say the derivative of sinus of x, just sinus of x. So this is just like sinus of t. Okay. So, and we'll just do like lean space, and we'll just go from 0 to like pi in like, yeah, kind of. Does this work this way? I think so. No? In like, what's lean space? NP lean space. Endpoint, no. Start, stop, and it's the number of steps. Okay. So I'll just say, you know, this is like, do that in like 100 steps. Okay, so it does like that. Or like, I don't know, 3 times pi, right? So we kind of see these. So basically what we're saying is like if the derivative at this point here, right? For example, it's 0, right? So what this is telling me is that derivative is like, so x plus pi divided by 2 and x minus pi divided by 2. Okay, so you take pi divided by 2, so that will be like roughly, you know, 1/2. So yeah, that would be like, I don't know. I mean, so if I'm at that point, that's roughly like 5 or like 4 dot something. And if I'm doing like pi divided by 2, so that it's like, it's basically what, like 1/2. So it's like 6 something, right? So, but like, let's say it's kind of here and kind of here. So you're kind of getting these 2 points, right? And so you're saying the derivative. Okay, so basically these derivatives are opposite always, right? So if you, whatever point you're taking at, like, so in this case, this derivative is going to be positive, this is going to be negative. Give me a second. Now, sorry, I'm stupid. It's not. It's not like it should be 0. So it's this point. Okay, no, okay, the idea, it's not, no, I'm phrasing it wrong. It's like, the points that are like plus pi halves and minus pi halves will actually be, or should actually be, the same. Because in this particular case, right, when you're here, because you're in the middle of a cycle, which is, you know, a cycle is like, is pi, right? So exactly. So if I'm here, that's the 0. That's the derivative here is 0. So if I'm here and I just go like half the cycle back and half forward, it's going to be the same. And so that's going to be 0 basically. If I am like at this point, so if I am like, say, at this point, Okay, so let's imagine I'm this point. Then half my cycle will be sort of the opposite as the other one. So that will actually turn to one. So basically what makes this possible is it's kind of funny really. It's the symmetry, right? It's the symmetry of the function that makes these possible. It feels like it feels like that's it. It's the symmetry of the function that makes that possible. And so what I would expect to see in something like when plotting the expectation value of a simple circuit is that I would sort of expect to see the same uh, or similar a similar thing. So why don't we just do that? Why don't we just like um, take for example, okay, what do we do? Do we pick Qiskit? We pick Qiskit maybe because I have everything installed, I think. So how do we import this thing? Um, mm, Qiskit. So import Qiskit, and then so just like import Qiskit, and so run this again. Oh no, now it's taking a long time again. We're playing 5 buffer messages. Restoring connection. There's something wrong with Jupyter, I think. Okay, now it seems to have worked. So what I want to do is I want to create a circuit that let's just say like has a just an RY rotation like a parametrized rotation. So it's gonna have like a um, oh, wait a second. Actually, I think Circ has some nice expectation value thing, but I think polystring, but I think Qiskit should also have these expectations. Snapshot expectation value. What is it doing? So of an operator. Okay, so actually mm, snapshot. What is a snapshot? Variance of probabilities, qubits, they set the qubits to snapshot. Um, the operator. Mm, Circ. Can we just go to Circ documentation? Expectation value. Expectation from state vector from density matrix. Cost function. That can be interesting. So here this, oh, that's the actual, okay, that's the actual tutorial. I remember doing that, where you get that and then creating the ansatz. Okay, I might as well just copy most of these code. Mm, print circuit simulation. Energy function. No, that's just too much. Mm, I don't know. To be honest, I forgot almost how to work with all of them. At that point, I'll just kind of like probably calculate the expectation value manually. So that will be just running, you know, just running multiple shots and get sort of the average. But let's just use circ because I want to refresh that a little bit. Let's just do some basic circuit, like how can I parameterize? So no, just let's start with gate circuits, simulation, noise, whatever. Import circ. Let's create these. And there's a gate and and I want to have a gate with parameters. And I had these. I had these in here, so let's just start with these a little easier. So we start with importing circ, or let's do it like import circ, and then we are doing basically not these but these. So we're doing the relational stuff. So we're doing just one qubit for now. So we're just doing one qubit. So we're doing one qubit, and then we're doing appending gate. So we're just gonna append a Y rotation, like a parametrized rotation. I feel that has changed a bit actually. Exponent half turns. How do I parameterize stuff? So over all repetitions. So this is the objective function. Sorry, the expectation value. Parameterizing the answers is what I wanted. Okay. Okay. So actually with SymPy, now I remember. So with SymPy, and then what are we doing? So we're doing you create a circuit. Okay, you just do like that. So you create a circuit. Okay, but now I don't know how this is done here. So what is this one step? What is this defined? Okay, so that's just defined as a rotation X layer. So okay, I get it. So basically, so what I will just do is I'll just probably get these function kind of work it out here. I'll just rotation, let's say Y. I just want to try with Y. And so it takes the Y POW gate and it just does these range length, yield rotation. Okay, that's what is okay. So that's the gate, and then that's the gate applied to the qubit. Man, I gotta refresh that stuff a lot. So if I do these circuit append, I remember I liked a lot the way you build circuits like that. And then I say length, basically. I know it's 1, but we'll just, and then this is basically alpha. And if I print the circuit, SymPy is not defined. Import SymPy as SP, and then we'll just call this SP. Okay, so that's what we got. Okay, cool. If I increase these to like 3, then we're gonna have, oh, why so many? It's a 3x3 grid. Okay, makes sense. So 1 by 1. And now what do we do? So what do we do? So what do I want to do now? I want to vary these, and I want to kind of calculate the expectation values and then just plot that, right? So if I just say that, so inputs is like lean space, say, from like, 0 till 2 times pi. So we'll just kind of use the full range of angles there, and then do this like in 100 steps, right? Cool. So what I want to do is basically I want to, how do they do this now? So not use these. How do they run these? We're pending, da da da. The circuit simulation, exactly. So run repetitions 100, 1 step measured. Okay, yeah, but how do we try different? So this is how you calculate. One can then calculate the expectation value over all repetitions. That's expectation value. No, parameters in the ansatz. Oh man, that's just what I did. Okay. A resolver. I want to sweep. Oh, here, there you go. So you have a sweep and then print the results. Of whatever object function. So you actually can, okay. So you can sweep through these, say, we just want to do actually, that is key alpha is what I have there. Start at like 0. Stop at like 2 times pi. Length like 100. So that is kind of creating these. Interesting, what is these doing though? And then get the simulator, which I need to still get. run a sweep. Okay, so that basically runs a sweep. And then if we want to print the result, let's see what we get. So how do I get the simulator set up and running? So the first part is, I totally forgot. It's just like that. Okay, Circ simulator. So I'll just, basically, you have the circuit. Here we have the simulator. Simulator equals circ. Simulator class, not simulator, it's simulator. So this is not needed. So we have this sweep, and then we print the results. What do we get? There's no measurements to sample. Circuit. How was this measurement thing? Measurement. Just measure. Circuits, gates. Oh, they've updated that a lot. Okay, cool. Circ measure. Okay, just like that. A, B. Measure. I guess I want to measure all the qubits, so I don't know if they... How do you add the measurements in here? Measure. Oh, just like that. Just like that, it penned all the qubits. Okay. Oh, okay, so now you have all the measures, all the measurements. Now I need the expectation value out of these. So we'll just kind of have to basically we'll just kind of have to calculate that. So what do they do here? So get the result, get the energy histogram. I don't know what is these, but like sum of all the items. Okay, just calculates an average. Reshape measurement to an array that matches grid shape. Convert it true or false to +1 -1. That's the key, right? Because it's the Z observable. We're calculating the expectation value of from. That returns the energy, because that kind of calculates the energy. That's not what I wanted to do. List of lists. Why does it have to be like these? I just want to calculate the average of each of these measurements. But it's funny because you can see, like, even just looking at the measurements, you can see there's like a pattern in here where it's like all zeros, and there as you move down, like you're getting to all ones, you're back to all zeros, back to all ones. Like, so there's a bit of these kind of like, symmetry that we saw with the sinus function a little bit, and I think that's kind of what we want to see as well. So what is each result? Like, what do we get as a result? So what's these object? What's result? Mm. Oh, so I can just do like these probably, and it's gonna be easier. How many zeros, how many ones? That's gonna be the easiest way to do that. Histogram key A. Key X, I guess that's what we want to do in invalid syntax. Y. This. Okay, so now we have the counters. Ah, okay, cool. So what we want to have is we want to, okay, so we want to just basically, okay, cool. So what we're doing is like, this is the result, okay? And so what we're now doing is basically the expectation value, the eval is like R zeroed, like this is basically the amount of, so what was that, like so true is +1 and zero is -1, so times -1 right, plus R1 times 1, which is redundant, and then so we're just summing them up and then divide it by like 100, right? And if I print eval, hey, that's the wrong way to, so I'll just call it expect, or just E, come on, just E. Oh, that's for error as well. Expectation value. Oh no, that's the, that's the average. What am I doing? Am I that stupid? The expectation value is the sum. Yeah, it's the sum by divided by repetitions. So, I mean, if I just like print these, what do I get? Okay, I'm just like, it's the wrong. Oh, there you go. There you go. There you go. Okay, so here we have the expectation values. Cool. And now if we just plot them all, so what I'm going to say is I want to have, so how does the, what is this sweep, by the way? Okay, so it's printing alpha, 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 blah, blah, blah. Okay, cool. So just basically like that. And if I just want the, I like those exact values, but I'm not so sure that's the, I don't really know how that's implemented structurally. So I'll just like say basically the inputs, I'll end up just using np linspace from 0 to, what do I say, 2 times np pot, and then 100. And so if I just now basically build a so I just now basically you know, data is just like np array, like an empty array, and then I just do like data append. Can I do something like that? Can I just, I need an index or some of some sort for result in results. Because I need the input and what else? That's it, no? So I just, I don't know. I don't want to. I'm just gonna do it the dummy way. So basically append. So inputs I, and in the actual expectation value, and at the end of that, can I do that? Append push, no push, append, so data equals np append, and I think that's the way you do it. Data, and then an np array with these. I think that's the way you do it. Is it? I don't know. Yeah, exactly. So if I turn that into an array, sorry, then I'll get like a matrix kind of, right? Because if I just say print data 0, then I'll just get, or can I just not print these anymore? No. I don't wanna append. I don't want to append. I just want to add np push array element, concatenate, insert, appended element, but I want to seems append is the right way to go, but that's so if I do reshape 2. Oh, it's just a long array. I just want to have like a data. Can I just like it cannot be that complicated. Okay, well, give me a second. How is this working? So I have lean space and then you're plotting the function, but I don't want to plot a function. What I want to plot in here is actually plotleap, a scatter plot, I think it's called, right? X, Y. Okay, so in separate arrays. Okay, that makes then sense. Then I can just I can just use these, and then it's easy because then I don't need to combine them. That's the point. So the only thing that I need that I need to do is I need to actually basically e values, and then I just kind of say, well, e values append. I'll just append these expectation value, and then print e values, and there you go. Append is np. Okay, so that should work. No. np array. Why is it empty? Well. Then I probably was just right at the very beginning. Okay, so we have these values, and we have the length of these is, and the length of inputs, it's both 100. That makes sense. And now I just do scatter plot. Where is the scatter plot? Scatter plot, scatter plot. So just scatter, I guess, because this is. So if I just do scatter, so if I just take the subplots, scatter plot example. So plt scatter, then just show. Okay, that's the way you do this. So you do plt scatter, and then you say inputs and e values, and then you say plt show. Yeah, there you go. There you go. Nice. So it actually looks like a sign, yeah, it really looks like. Now, question is, how can I make a okay, let's change that. Let's change these by an X gate, for example. Sorry. Just call it rotation layer. And then we're gonna change this like that. And what about like an X one? It's the same. What about like Z1? Well, that's just like that. Okay, so that makes no sense. But if yeah, because this is a gate. Interesting. Interesting. I mean, it's like if they have the shape, then it kind of, yeah, it makes sense, right? Now the question is what happens if you know, as you increase the angles, right? It's interesting. So what if we, not increase angles, what if we increase the qubits? So let's try to do 2 qubits. So if I do these, it's gonna create a 4 qubit kind of thing, and that's not what I want. What I want to do, is I want to just have 2 qubits. So I'm just gonna measure. That's bad. So I'm gonna call length 2, and then I'm just gonna have 1 dimension, and so this is gonna be always 0, and this is gonna be always I. So okay, what else am I using length though? Not square, but like a line. Qubit has no attribute line. Is it line qubit? Is there this concept? Just no, actually it can still be, no, it can still be Greek qubit. I just want these to be up. I just want these to be, you know, in a Greek qubit in call. Okay, just like that. So what if I just what if I just hard code that? Like what if it's just like qubits is like oh, it's a Greek qubit of, okay, so I can just say Greek qubit of like 1/2. Control not a Greek qubit. Neutral. Okay. How do I do that though? So square. Okay, just a rectangular rows and calls. I can just do it like that. Okay, rect rows and calls. Okay, cool. So I'll just call it like rectangular rows, 1 row, 2 columns. There we go. Cool. So we have 2 things that we're measuring. And now I want to kind of have like another symbol. And I want to have these called beta. And what I want to do now is I am doing the measurements. I also want to sweep independently beta. So it's going to be sweep. How do I do these? So how do I sweep? Can I sweep 2 variable? First, let's simplify that. Okay, let's just make sure that we use just 1 sweep, and then sweep. So maybe there's just an example somewhere here. How can I sweep across multiple keys? Sweep angle countables. Synthesize the symbols for sweep. Oh, it's a param resolver. Okay. So there's the maybe there's just, you know, maybe there's just a way I can do that. Key, just one key. Linear space sweep for a given key. I want to have multiple keys. Can I least sweep? How do I sweep over multiple parameters? So how does this make sense? Maybe I should just okay, maybe what if I just use the same symbol for both? Let's do it this way. So, okay, that's cool. Alpha, blah, blah, blah. But then like the rotation layer, it's all alphas. Actually, it's already like that, alpha, alpha. Okay, that makes sense. Alpha, alpha. Okay, so that's fine. So it's just one sweep for one parameter. We're gonna keep it the same parameters. Just I want to get it like 3D, and then we'll see if we can kind of like vary the parameters as well. You know, if we kind of get a similar idea. What am I doing now? So I have these. I'm sweeping and I'm running all this kind of stuff, and I don't wanna show this for a second. For a second, I'm reading these, and what am I key X. What I'm now actually, if I print R, the problem is now I get like 0, 1, and yeah, I can get like, you know, any of the 4 combinations. And so what are the expectation values of those, right? That's the key. But it's a similar pattern. You see, like it goes from like 100 to like 100. Like you can see this pattern already here, that it kind of also has this sort of symmetry. Okay, we'll get to these. I think that's roughly right. What I want to do next with next session is maybe explore that more in a 3D kind of style. I just wanted to keep this video under the hour. I want to see how can I sweep like, you know, a multiple keys at the same time, and then kind of like do a 3D scatter plot of stuff like this. But I need to figure out how do I calculate the expectation value of those things here of multi-qubits. Like, is it just like the multiplication of each separate? I don't know. I guess so. Like you know, 1 1 would be like +1 +1, right? So 1. I think so. And then and what I want to do afterwards is I want to do what I got as a suggestion. So from Bruno, right? Where it's like, hey, he thinks QAO is very nice. So I will probably do so. I will probably do that. So I'll try to do the 3D thing, and then I'll try to get like a QAOA example, maybe with 2 qubits as well, and see how this looks like. What is anyhow different? But we're getting this symmetry, so that kind of basically tells me that's just the reason why the parameter sheaf rule works, and why we can actually do these in VQE. So yeah, but you can see here the pattern already. with the counters. You can see that it's funny because it's not only that, you actually see a pattern in terms of the types of answers you're getting. Like here, it's like more spread out in the middle, right? 0, 2, 1, and 3. So it's not just in the, it's really across the whole system that you're getting this symmetry, this symmetric pattern in here that basically is gonna, yeah, that's what tells you that. It's interesting. I don't know mathematically whether there's any curiosity behind this, but I'll probably do some reading around this. Cool. I thought it was. I hope it was nice. I like this kind of exploration videos as well from time to time, and I'm refreshing some of the my Circ skills, which are almost non-existent. Goodbye.